Okay, got another one for you here. Very different from the previous one. And I'll tell you after we're done why this is one of maybe the most important function in the world. And I think I can back that up. So let's see what it ends up looking like. E to the negative x squared. So here we go. Same thing that we did last time. And by the way, as I say, I'll be doing half dozen of these or so. And what I'd suggest is, as you get good at it, feel free to, again, stop the video and see once how much of this you can do on your own. I'm going to be doing the same things each time. And so see once what you can figure out. So first of all, the domain. The exponential function, e to the x, that accepts everything. And x squared accepts everything. So there's no restrictions at all there. And so we can say from minus infinity to infinity. There we go. Intercepts. Well, let's see. To get the y-intercept, we go f of 0. F of 0 is going to be e to the 0, which is 1. So the y-intercept is 0, 1. X-intercept. Well, let's see. Recall that the exponential function never hits the x-axis. So it doesn't matter what's up there, e to anything is always going to be a positive number. So there are no x-intercepts. So we can say y-intercept is 0, 1, and x, none. Okay, I think that looks better than this. Okay, very good. None. Just have to spell none right. Very good. Okay. What's next? Symmetries. So recall what we do. We take f of negative x and see what the function looks like when every place there's an x we put a negative x. So we're going to get e to the minus of a negative x quantity squared. Negative x times negative x, the negatives go away. I still have this negative out front, but those two negatives cancel, and I just end up with x squared. And look at there, e to the negative x squared gives me back by the same function again. That's f of x. And whenever f of negative x gives you the same thing as f of x, you've got yourself an even function. So symmetric with respect to the y-axis, which means it's even. Okay, good to know. Asymptotes. Asymptotes. Okay, so remember to get vertical asymptotes, we ask, are there any places basically where you have a denominator that's going to 0 or an ln function? Those are the places where you would have a vertical asymptote. There are no places like that here. So no vertical. So let's say vertical, none. And horizontal, all what to do there. We take the limit of e to the negative x squared as x goes to infinity. Well, what's that going to be? X gets bigger and bigger and bigger. As x gets bigger, this becomes a really big positive number. With a negative there, it's going to be a big negative number. By the way, it should be very clear that when you have a square there and a negative there, it means that you first square it and then you take the negative. So you square it and then take the negative. So this is always positive. This will always make it then positive. So what happens is you take e to a big this is positive. When you take the negative, it becomes negative. So what happens is you take e to a big negative number. Well, here's the graph of e to the x right here. As you take e to a big negative number, it's going down towards 0. So that limit is 0. Similarly, if you go to minus infinity, then the same thing happens. Well, actually, we know that whatever it does on one side, it's going to do the same thing on the other side. So we already have that just from the fact that it's an even function. So the limits are both going to be 0. And the reason is the same. You put in a big negative number or square it, it's a big positive number. By the time you're done with this, you still have a big negative number. E to a big negative number is going to 0. So horizontal asymptote, we could say y is equal to 0 is the actual asymptote. Okay, very good. So we did all that stuff fairly quickly. And so now we can get into the calculus. There's 1, 2, I guess the other thing that came with intercepts is, where's the function positive or negative? Let's do that right here. So there's no places where the function is 0 because there are no x-intercepts. So apparently, either this function is always positive or it's always negative. I guess we mentioned already, e to anything is always positive. So it doesn't hurt just to put that there, just to remind you that this function should always be positive. E to anything is always positive. Okay, very good. So now let's go ahead and do the increasing decreasing. And recall that's where the derivative is either positive or negative. So we'll take the derivative. I'll do it slowly. See if you can stay ahead of me in your own thinking. If you're following along with pencil and paper, give you a chance to get ahead of me. The derivative of e to anything is e to that thing. The derivative of e to anything is e to that thing times the derivative of that thing. So I have to take the derivative of negative x squared. And I left a little space for it out front. The derivative of negative x squared is negative 2x. So there you go. There's your chain rule. The derivative of e to anything is e to that thing times the derivative of the top of that thing. So there you go. So now we want to know, when will that be 0? When will that be 0? Well, e to anything, we already said, is always positive. So the only time that's going to be 0 is when x is 0. So here we can make ourselves a number line again. Put in the one spot where it's 0 right there. And then check it out on both sides of 0. Again, it's a continuous function. So all we have to do is check one value here, and it's never going to cross. In fact, it's never going to cross the x-axis at all because it's always positive. So we don't have to worry about that. But I'm sorry, but the derivative is going to cross. Let's see what happens. The derivative is going to be what? If you stick in a positive number here, a positive number for x, e to that is always going to be positive. This will be positive. This will be negative. Negative times positive is negative. So the derivative is going to be negative. What about on this side? On this side, what's happening? The function is positive. This thing is negative because we're over here is negative, and this is negative. Negative times negative is positive. Positive is going to be positive. So this is the derivative we're talking about. This was f. That's f. This is f prime right here. Okay, so what's true? If the derivative is positive, that means the function is increasing. Actually, it's strictly increasing, but usually just to write increasing gives you the information you need. And the derivative is negative here, so it is decreasing. Okay, in fact, strictly decreasing. So it looks like that. And so we're getting all the information we need. Now the last thing is to find where it's concave up and down. So let's go concavity. Okay, for the concavity we need the second derivative. So the second derivative, here we go. Recall we have to use the product rule here. So the derivative of the first thing, which is negative 2, times the second thing, just the way it sits, plus the first thing, just the way it sits, times the derivative of the second thing. What is the derivative of this thing? Well, that's what I took the derivative of right here. The derivative of this is this whole thing. See that? The derivative of this is this whole thing. So I got to put this whole thing down here now. I've already got a negative 2x, but here's another negative 2x. So I square that, and then I need this as well. Very good. There you are. So that whole thing, we want to find out when that's equal to 0. So we might as well factor out some common stuff here. Notice that I have an e to the negative x squared that I can factor out of everything. And after I've done that, what do I have left? Negative 2 times negative 2 is going to be 4, so it's going to be 4x squared. And then here it's going to be minus 2. Like so. So we want to know, when is that going to be equal to 0? So let's see, this will never be equal to 0, so we just need to know when this is equal to 0. How can we do that? Maybe the easiest way is to, let's just go up here and go 4x squared minus 2 is equal to 0, which means that 4x squared has to be equal to negative 2. Is positive 2, rather. Okay, if this quantity is equal to 0, that means that 4x squared has to be positive 2. Divide both sides by 2, and you get x squared is equal to, or divide both sides by 4, rather, and you're going to get x squared is equal to 1/2. And so x is equal to the square root of 1/2. And the square root of 1/2 is the square root of the top divided by the square root of the bottom. And you have both the positive and the negative square root. So those are the places right there where the second derivative is going to be 0. Negative 1 over square root of 2 and positive 1 over square root of 2. Okay? So now we have to check all sides of them. I really haven't factored this. I could have factored that all out, but since I haven't, we can still use this easily enough. If I stick in a number greater than this, I just want a number obviously greater than that. How about 150? Put in 150, square it, multiply it by 4, subtract 2. It's going to be positive. That's also always positive. Positive times positive is positive. What's a nice, easy number in there? 0 is pretty convenient, isn't it? So put a 0 in here. You're going to get 0 minus 2 is negative. Negative times positive is negative. And then finally throw in negative 150 if you want. Negative 150 squared is going to be a big positive number. Positive, subtract 2, it's still positive, positive. So the whole thing is positive. There you go. So again, be really clear, this is f double prime you're talking about. So this thing here told us increasing, decreasing. This thing here is going to tell us that it's concave up, concave down, and concave up again. So it'd be nice if I had a little longer board, but I think we can do it here. Okay, let's graph it. Key points, 0, 1 is on there. Once you pass 1, what's happening? It is once you pass 0, what's happening? First of all, it's decreasing. Decreasing all the way. It's going to be concave down initially. Concave down means it lies below the tangent line. But then, eventually, it becomes concave up. It's still decreasing, concave up, and it never goes below the x-axis, never even touches it. So that's the asymptote. So it looks something like that. And right there is 1 over the square root of 2. That's where you have your inflection point. It's concave down on this side, concave up on that side. It's an even function, so once you have one side, you know exactly what the other side is going to be. Something like that, if I drew it well. Negative 1 over square root of 2. Okay? And so you can, if you want to, you can put these values into the function. If you do, you're going to get 1 over square root of 2 squared is going to be 1/2. E to the negative 1/2. E to the negative 1/2 power means 1 over e to the 1/2 power, which is the same as 1 over square root of e. Whoops, square root of e. So this height right there is, let me do it like this. that height right there is 1 over the square root of e. Okay. Now, as I told you, this is perhaps the most important function in the world. And the reason why is you've maybe heard the term bell-shaped curve. Sometimes you hear the term Gaussian distribution, normal curve, bell-shaped curve, I guess I mentioned that. This is the curve that they're talking about when they talk about your typical bell-shaped curve. All sorts of things in the natural world, if you're looking at people's heights, at intelligences, IQ tests, if you're looking at speeds of molecules, if you're looking at anything where you just kind of count a lot of things that happen, it very, very often develops into a bell-shaped curve. I have a fun little thing at the office that just a whole bunch of little balls come down and hit a bunch of pegs, and every time it hits a peg, it either goes this way or this way, and by the time it gets to the bottom, it's developed all these little marbles have made a bell-shaped curve. Okay, too bad I've got that at the office, but anyway, it shows up a lot in statistics and probability. So that's a very important function. And it turns out the area under that is a finite area. And so when you're trying to figure out the probabilities of things, you're often trying to figure out what's the probability that your height is between here and here, or that sort of thing. What percentile are you in? You ask about little kids and you find out what quartile they're in. They're quite often it's roughly a bell-shaped curve that things are in. Okay, very good. So this is e to the negative x squared, and we'll do another one in our next lesson.